Hi everyone, here we are in chapter 12. We are in section 12.7 and this is example number 4. So we have a cyclist that travels around a horizontal circular path with a velocity of 0.09 t squared plus 0.1 t meter over second. So we are given the expression for the velocity and we are asked to find the velocity and the acceleration for when it has already covered 3 meters. So we have, see, this is the starting point, or this was the starting point, let's say, t equals 0. Here is starting 1, so it has covered 3, s equals 3 meters. So, what do? We have the velocity in terms of time, and we have the position. So, what we have to do then, we recall that the velocity is the derivative of the position respect to time. Since we are given the expression for the velocity, we will have that we can integrate these expressions. The limit of integrations will depend on the differential, right? So this is 0 to a certain time, and this is, it says that we can put that is our 0 to 3 meters. So we integrate this expression and we get that and this is, I integrate that and that's just s in 3. So here we integrate this expression and we get that this is 0.09 t cubed over 3 plus 0.t t squared over 2, all that evaluated between 0 and t, and s we already can evaluate it. This gives me an expression which the only unknown is time, right? So it's 0.03 t cubed plus 0.05 t squared equals 3. This expression sometimes is a little bit hard to solve for t, but there is several ways to do it. You can even solve it by iterative process, or you can graph the equation, or you can use a calculator. So I am not going to solve that. You can look for different methods. One of them is solving for t and then put a t in the other side of the equation and recursive iterations, and you get t. For solving for t, I have the result, and the result for t is equals to 4.147 seconds. So once we have solved for t, then it's easy because we are asked to find the velocity, and the velocity is already given. So remember then, so substituting velocity for t equals 4.147, then the velocity is equals to 0.09 4.147 squared plus 0.1 times 4.147, and that gives me the velocity, which I also have it here, is 1.96 meters over square. So this is in magnitude, right? If we want to put it as a vector, remember that the velocity is always tangent to the trajectory. Okay, so that was the velocity. Let's do the acceleration. So well, remember that if we have a circular path, we have acceleration in 2 directions always. Tangent acceleration and normal acceleration. So those 2 are perpendicular. Obviously, if you look at that from the top, you will see that those are perpendicular. One is parallel to the path, and the other ones always point towards the radius of curvature, which is 10 meters. So we remember then that the acceleration is a vector of 2 components with tangent acceleration in the tangent direction plus normal acceleration in the normal acceleration. And we remember too that the tangent acceleration is the derivative of the velocity, and the normal acceleration is the velocity squared over radius of curvature. And the velocity we already have, the radius of curvature is given is 10 meters, so the only thing that we need to find is the derivative of the velocity. Since we are given the expression for the velocity in terms of time, so then we have that the tangent acceleration is the derivative of the velocity in respect to time, and that's the derivative of this expression right here, which is 0.09 times 2d, right? Plus 0.1. And then we can evaluate that for t equals 4.1, this is seconds, 4.147 seconds. We have the tangent acceleration. I have it right here. Let me place it right there, 0.8465. Then, with that, we can say that the acceleration is equals to this value right here, this is meters over second square, 0.8465 in the direction, plus this expression right here, which will be 1.96 square over the radius of curvature, and we are given that number is 10 in the normal direction. So that will be my, let me place the results in a different color so that we know where we have to calculate. So this is the vector form, and if we want to have it as a magnitude, we remember that as a magnitude we have the square root of the tangent acceleration plus the normal acceleration. And if we plug this value here and this value over here, we get that that's the square root of 0.8465 square. This value over here is 0.3852 square. And finally, we know that we can calculate that the acceleration is 0.930, and it's very important to put the units as meters over second square, and that's the magnitude. Let me add here also the units, meters over second square. So we were able to calculate the velocity and the acceleration for 3 meters in terms of a magnitude, a vector, and a magnitude.